you find yourself getting stuck, you have people around you to talk to. If you find yourself getting very stuck and you'd like me to just come around and talk to you, go ahead and raise your hand and I'll come around. Cool. People feeling pretty okay? All right, well I certainly didn't do the walk, so tell me, what is this result of division? By some it looked like people at least agreeing with each other, so I think people have like an answer already.
1.1 plus -7 over 10i.
Minus, you said 7 over 10?
Yep.
Cool, I'm going to put it all in decimal form just for consistency's sake. 1.1 minus 0.7i. People agree or disagree? Agree? Any disagree? Cool. So instead of, well, do people want me to actually talk through the walk of doing the division? Is there a demand? Cool, then I will. So what's the trick in doing complex division? Like what's the first step that you did in the process of getting that result? Yeah.
Did you have to multiply the top by the denominator? So multiply the whole thing by the denominator?
Not quite just the denominator, the complex conjugate of the denominator. Because you're going to multiply and divide. So the trick whenever you're walking with a fraction and the denominator is complicated is you want to multiply by 1, because that doesn't change the number. But you want to multiply by 1 in a way that makes the denominator less bad. So let's try to do that.
So let's multiply and divide by the complex conjugate. Complex conjugate of the denominator is 3 minus I. And right, you can always multiply and divide by any single thing. Like that could be 12 over 12, and like that would be a correct step. But I think this is the helpful version of the correct step. The reason to do that is now you know for a fact the denominator will be real. And I guess now you just have to FOIL out both the top and bottom. I suppose I can go through those motions. Weird enough, I'll probably screw it up. 12 minus 4i minus 3i. Gosh, this is lots of negatives. Double negative, so plus I squared. All over 3 times 3 is 9, minus 3i plus 3i minus I squared. So far, so good. In fact, how many people like skip the step that I just wrote because you already knew what the denominator had to be? Yeah, right. We have a formula that says when you multiply a number by its complex conjugate, you always get a squared plus b squared. So I know the bottom should be 9 plus 1, which hopefully it is actually. So let's see. Those cancel. I knew they had to. Minus I squared is the same as plus 1, plus I squared is the same as minus 1. So, carrying on, I get 12 minus 1 is 11, minus 7i, all over 9 plus 1 is 10, and yeah, that looks like the result of dividing by 10. So whenever you want to divide by a complex number, it's too difficult to do directly, simplify the denominator, turn it into a real number, then do the division because you know how to divide by a real. In fact, in this case, it's very easy to divide because it's just 10. Nice. Let's talk about how you can check this answer. What's something you can do to check that this division is correct?
division mean? Division is like anti-multiplication. So if I take the thing that we just found and I multiply it by the denominator, I should get the numerator? Yeah.
So, in order to check this, let's do 1.1 minus 0.7 I, parentheses in the wrong place, I, multiplied by the denominator, 3 plus I. Is that equal to 4 minus I?
And maybe I'll pull back the curtain a little bit farther. Right, if you were to have to do division an awful lot of times on your own, you'd resort to a machine, right? Your calculator probably doesn't do complex arithmetic, though I don't know. How many people's calculator does do complex arithmetic? Alright, cool.
I'm going to at least check this multiplication using a machine because, it's worth knowing that you can. Let's see, I think the Google calculator is even good enough to do this. 1.1 minus 0.7 times I times 3 plus I. 4 minus I is the end result. About what it should be. Awesome. So there's a way to check.
There are other things, anything you can do with real numbers that don't involve inequality, you can do with complex numbers. For instance, you can take square roots of positive real numbers. And now that you have complex numbers, you can take square roots of negative numbers, right? We'll just get an I. Turns out you can take a square root of any complex number. If you want to walk out the details, extra credit, theoretically at the end of this section of the notes, but it's online only just because I didn't want to print something that maybe not everyone would look at.
Last thing I want to do in here. What's the whole point of introducing complex numbers? It's so I can write down the quadratic formula for degree 2 polynomials. The point is the quadratic formula still works. So I think I'm going to write down the quadratic formula, then I'll solve, then I'll jump down here. So we have a quadratic formula, right? What's the formula for the solution to this equation? I want someone to say it, like you're all writing it. I guess I could just do that too. Okay. Negative b plus or minus square root b squared minus 4ac all over 2a.
And right, if you're the type of person who doesn't like to remember a formula like that, remember how to complete the square instead. Once you complete the square, you can solve a degree 2 polynomial equation directly. It'll hand you the quadratic formula. In fact, there's an extra credit in these notes that has you do exactly that. The point is that formula still works even when that thing under the square root is negative. And let's just see this demoed. X squared plus 2x plus 2. That look like something we can solve? Yeah. And maybe we'll do it two ways. Let's do it. We'll use the quadratic formula on the left, and on the right, we'll complete the square, because completing the square, we'll really see where that imaginary bit comes from. So using the quadratic formula, x equals negative b plus or minus the square root b squared minus 4 times a times c all over 2a. Plug everything in correctly? All right, so now it's just a matter of evaluating. And I guess it's sensible to start under that square root? Yeah.
It should be 2a. Oh wait, no, never mind.
Yeah, day is 1, so I think we're okay, right? Awesome. So, that is absolutely the type of thing that I would accidentally leave out if I'm not careful, but I think this time I'm okay. All right. Start under the square root. That's 4 minus 8, so negative 4 under the square root. Ooh, we see a negative under our square root. So here's what I'll propose doing with negatives under a square root. We have a square root for negative 1 now. It's I. So whenever you see a negative under a square root, well, a negative, negative 1, is a perfect square. It's I squared. So I'll split that up as negative 2 plus or minus square root of negative 1 times the square root of 4 all over 2. And what's the square root of negative 1? Unless you're an electrical engineer, in which case it's j. What's the square root of 4? 2, regardless of whether or not you're an electrical engineer. So, negative 2 plus or minus I times 2 all over 2. Any simplifying? I guess any further simplifying. All of that was simplifying.
Negative 1 plus or minus I.
Nice. So, we still get 2 roots for this quadratic equation. They just happen to not be real. That means that if you want to graph this thing, you won't see these roots. Because limitations of how many dimensions we have access to generally prevent us from graphing complex things. Right, like a complex number has like 2 dimensions worth of information in it. So to plot a complex function, you need 2 dimensions of inputs and 2 dimensions of outputs. That gives you 4 dimensions. That's like between 1 and 2 more dimensions than I can easily draw a picture of that. There are strategies, right? You can the input is going to be like the 2 dimensions on a plane. The output you can model by 2 dimensions worth of colors. You'll get things called like heat maps of complex functions. They result in really pretty pictures that tell you good information about the function. I just won't do that here. Let's do this one other way. Let's complete the square and then we'll actually see this I showing up naturally instead of as a consequence of just what the quadratic formula says. So if you complete the square on this thing, so let's see, this is x squared plus 2x plus 2. So what's this game for completing the square? I want to see x plus b squared showing up. So maybe I'll just remind myself x plus b, and then you square it, that'll be x squared plus 2bx plus 1, plus b squared. So the x squareds already match up, that's good. I don't have to do any of this stuff where you divide both sides by whatever that coefficient is. I need this 2bx to match up with that 2x, so what seems like a good choice for b? 1. So it sure looks like I want b equals 1. That means I need to see a plus 1 at the end. Do I see a plus 1 at the end of this equation? I mean, either the answer yes or no would be correct in my mind, because 2 is 1 plus 1. So you do see a plus 1, you just see an extra plus 1. So if you do that, this is the same thing as x squared plus 2x plus 1 plus 1. I'll put some helpful parentheses here because now that is a perfect square. And I want to set that equal to 0 and solve. That's now automatic to solve. Well, algebraic to solve. You don't have to use a fancy formula. If you saw that and you wanted to solve it, what would you do? Just start by subtracting 1. X plus 1 squared equals negative 1. What next? What undoes that square? Square root at a cost of a plus or minus. X plus 1 equals plus or minus square root of negative 1. Oh, that's plus or minus I. And now what do you do to just finish getting x on its own?
Subtract 1.
Oh, neat. So we get the same result we knew we should. And where did that I come from? It came from when we did completing the square, that negative on the other side of the equation. Nice. So what's the point here? Quadratic formula still works, completing the square still works. You can get a complex number out of it though.
And the last observation is, the thing that controls whether or not your answer is going to wind up being complex is that bit I just underlined in blue. The thing under the square root. So, here's the definition. The discriminant of a degree 2 polynomial is defined to be b squared minus 4ac. I'm just defining that to be the discriminant. When I talk about the discriminant of a degree 2 polynomial, that's what I have. It's called the discriminant because it discriminates between the cases of real roots, complex roots, and just one root. And there's no deep thought here. Let's just read off what those cases are. Let's suppose the discriminant is positive. So the thing underlined in blue is positive. Now let's just finish this sentence. ax squared plus bx plus c, how many roots will it have if that thing in blue is positive? 2. Because it matters whether I add or subtract, so I should get 2 different solutions. Real or non-real? Real. Which are real. If the discriminant is negative, then same sentence. So if the thing underneath the square root is equal to 0, well, let's run it through. What's the square root of 0? Doesn't matter if you add or subtract 0. So how many roots? Just 1. Has 1 solution. And maybe I'll drop a buzzword here. This is a solution of multiplicity 2, which is real or non-real? All right. The case that the discriminant is negative. If the thing underneath the square root is negative, then same questions. How many roots do you wind up with? 2. You wind up with an imaginary number after you take that square root. It matters whether you add or subtract it. You'll have 2 solutions, which are real or complex? Complex. And maybe I'll even be a bit of a pedant here. Every real number is also complex, so maybe a better answer here is non-real. Also, notice those 2 answers, they're the same answer except that they're imaginary bit. One of them's positive, the other one's negative. Oh, they're complex conjugates of each other. If you multiply the 2 roots by each other, you'll get something real. That's handy. If you add the roots together, you'll still get something real. All right, that feel pretty okay? All right, let's just do one quick classification problem, and this will be pretty light too. Oh, I fixed this typo. There's some redundancy there. That's the same question twice. So let's apply that idea here. I'll remind you what the discriminant is. Discriminant is b squared minus 4ac. So let's use that tool to play this game. So without actually finding the solutions, 3x squared minus 4x plus 2, how many solutions does it have? So the game here, I guess, is compute the discriminant and determine whether it's positive, negative, or 0. Feel that seemed like a sensible plan of attack. And it's certainly less work than finding the actual roots. Let's compute the discriminant. The discriminant is b squared minus 4 times a times c. And now I just need to answer the question, is that positive, negative, or 0? Well, it's a positive minus a negative, so it's 2 numbers fighting. Which one wins? Positive 1 or negative 1? The negative is bigger. Right, because the negative is, they both have a 4 next to them, and the 6 beats the 4. Or you can actually compute it and determine what negative number it is. Yeah,
I think I got -8.
that sounds right. On the other hand, you could say, well, that's already 12 times 2, so that's definitely bigger than 16. So you don't need to do the computation in all detail. All right, so discriminant's negative. What does that tell you? Two, and I'm going to be a pedant. If you write complex solutions on like the test, I'll be fine because I know you mean not real when you say complex. But really, every real number is complex. So I'm going to put non-real there just to make the strongest possible statement. Think you could do the other two based on this idea? All right, take a moment. Compute some more discriminants. Compare with those around you. I guess I also get that, like, I had the example in front of you for long enough that some people maybe did that while I was just talking. Cool. People feel like they have it? So let's just answer the question and then we'll fill in the blanks of how you got that afterward. So that second one, the one at the top of the page. How many roots does it have? Are they real or non-real? Real? How many? One. Just one real solution? People agree? All right. One real solution. So that means you computed the discriminant or did something to the discriminant, and what did you get it to be equal to? Ruby. Anyone want me to write any of those steps that I've now completely suppressed? Nice. The second one. The bottom one. That one. I guess if I've designed this well, there should be two real solutions in this case. Did it work out that way? All right, no guarantee that I design things well, but it's nice when that happens. So what does that mean about the discriminant? How did it work out? Say louder.
It's greater than 0.
It was greater than 0. And people found that by actually computing it and saying exactly what number it is. Cool. What number did it work out to be? That is definitely bigger than 0. Nice. So, two real solutions. Notice the discriminant doesn't tell you if the solutions are like positive or negative. You need something more subtle than that to figure that out. We'll get such a tool in the next couple of days in the form of Descartes' law of signs. But we're not going to talk about that today. So that concludes like the stuff that I want to say just about degree 2 polynomials. Let's talk about what you can do even when the polynomials are higher degree than 2. Now I'm going to bust out that new pack of notes, now that we're 30 minutes in. So, polynomials of high degree.
So what's the goal today? Well, this whole section, so I guess today and probably half of Monday, is going to be based around the idea of like, how do high degree polynomials come up? What are they? How can you talk about their graphs? How can you make some progress on like solving? So let's start with an example where they just come up. So here's a modeling problem. So let's suppose you want to build yourself a box. You're going to build this box by starting with a pre-machined 3x2 sheet of cardboard. You're going to make a square cut at each corner. Maybe you won't actually cut them out, so you have like some flaps to hold. Stability would probably be good. So you're going to make these little cuts or folds. Then you're going to fold up those flaps that you'll wind up with. And what you'll wind up with is a box. So you're going to take this. After you make those cuts, you're going to fold here. You're going to fold there. And these like fold diagrams are always impossible to read. You're going to fold all those up, you'll wind up with a box. Let's just answer this question. Well, maybe you want to like make an optimal choice. You want to maximize the volume of the box you build. That seems like a reasonable goal. So I guess that means you want to like determine what the volume of this box is depending on the size of cut you make, because that's like the only choice you make here. Well, let's try to figure out the volume of that box. What's the formula for volume of box? Dimension times dimension times dimension, and what you call them is what you call them. Length times width times height. So, the formula for the volume of a box is length times width times height. All right. So, let's figure out what the length, width, and height of this box are. So I guess the width of the box is going to be like that length. So you're going to fold these flaps up. So from that picture, could you tell me what the width of this box is going to be?
3 minus 2x.
I got 3 minus 2x. Right, the total box is 3 wide. I forget what inches I gave. And then you cut 2 x's out of it. So this length is the width. It is 3 minus 2x. 3 minus 2x. Width. So I guess the width is that dimension. Same question again. I guess the answer is even pretty close to the same too, right? What's the starting width of this box? 2. I'm going to cut 2 x's out. 2 minus 2x. 2 minus 2x. And the last thing I need is the height. What's the height of that box? Just x. All right, this length that you fold up is the height. Oh, nice. Is that enough information that you can now just write down the volume of the box? It's the product of those things. So it sure looks like the volume is x times 3 minus 2x times 2 minus 2x. And let's suppose you wanted to do something like determine the maximum volume that you could get. Like what choice of x should you make to maximize volume? We don't have like a vortex formula for a degree 3 polynomial. Could we still do something to try to maximize? Like if I just asked you, determine about what x value maximizes the volume, what's something you could do? Seem like something you could have a computer graph? Yeah, I don't know how to graph it by hand, which is fine. We will be able to graph this by hand by the end of today. Well, by the end of this section of the notes. So let's pull up that graph. X times
3 minus 2x. If you have your own graphing calculator, you can do this along with. All right, there's the graph of the thing. And I see some weirdness going on. Certainly if this y-coordinate is volume, I don't expect a negative volume, but x also can't be negative. I can't anti-cut out of the box. So you start making the cut, the volume goes up, it goes back down. Well, something weird happens when x is 1, the volume becomes negative for a bit. Now, so what's the explanation there? Like, why is that like not allowed? What's the biggest that x could possibly be? 1. Right, if I cut bigger than 1, then there's like nothing left on this side. I can't make a box then. Like cut away all of the width. Yeah, so this negative volume just corresponds to the problem, doesn't even make sense. And certainly then like none of these values make sense. I've cut away all of the width and all of the length. So it looks like just from 0 to 1 is the domain. By looking at that, about what x value seems to maximize this? Yeah, like 0.4-ish, I guess is the best you can do without like me clicking on that dot. So it looks like this maximizes at about 0.4-ish. And it looks like the maximum value is a little bit bigger than 1. Max volume is about 1.05 with x about 0.4. Cool. So high degree polynomials just naturally come up. In this case, degree 3 polynomials come up all the time because we generally live in a dimension 3 world. If you're a physicist, maybe you object to me claiming that our world is dimension 3 instead of like 17, but whatever. So let's just now talk very broad strokes about what a polynomial even is. So we've already seen some, like a degree 2 polynomial is a quadratic function. It's a function of the form ax squared plus bx plus c. Right, the stuff we've been studying for the past little bit more than a week. If that's a degree 2 polynomial, what would you want a degree 1 polynomial to mean? Yeah, so this is like a linear term plus a constant term. With a and b constants. What would you want a degree 0 polynomial to mean? Just like the constant term? So like f of x equals 7 is a degree 0 polynomial. Linear things that have some actual slope are degree 1. Quadratic functions with a non-zero thing in front of the x squared are degree 2 polynomials. Now let's go the other way. What would you want a degree 3 polynomial to mean?
Ax cubed plus bx squared plus cx.
And maybe a constant term too. Degree 4 polynomial, same thing. And you'll notice that like the pattern I'm following is going to kind of break down once I make it to like a degree 27 polynomial. I'll run out of letters. But that's fine. If you have a sum that's that long, you want a different notation for it anyway. So maybe I'll write down something, a few different ways for a polynomial. In general, a polynomial is a sum of some coefficients multiplied by positive powers of x, and because of the way I wrote it, plus a constant term. That agree with all the things above? they're sums of some coefficients next to powers of x. The things in the powers are positive whole numbers. So that's what a polynomial is. So if you write down a polynomial, it'll be a coefficient times x to a power plus a coefficient times x to a power plus plus a constant term. So all those a sub i's are just supposed to be coefficients. This now just gives you a notation that lets you write down a polynomial without running out of letters in the alphabet. Each of those a sub d's is just a number. I guess this goes up to d many terms total, whatever d is. And sometimes it's nice to have a notation for that that's more compact. So this is the sum from k equals 1 to d. So this is that Greek letter sigma is chosen because that's the same as the first letter of the word sum. So the Greek letter sigma is used by mathematicians when they want to indicate a sum. Indexed by some variable k that starts at 0 and goes all the way up to d of ak times x to the k. And that's just now a more compact notation. I guess, I don't know, how many people in here have taken some sort of programming class at some point in their life? Yeah, you should think of that as being like instructions to run a loop, and each time you go through the loop, you add a coefficient times the power of x to the sum. I won't use that notation much because generally the polynomials we'll study will max out at like degree 5. So you'll just write out all the terms. Cool. There will be, however, plenty of instances in your life where you'll have sums that are too long to write out all the terms of. And so you write this summation notation, and then if you actually want to compute the sum, you tell the computer to compute the sum. Or you think hard about what the sum should be without computing all of the terms one at a time. Nice. So, we have these things called polynomials. They're sums of coefficients times powers of x. And the powers of x have to be non-negative whole numbers. So with that in mind, here are like 7 functions. I've added one in pink. Let's just answer some yes-no questions. Are they polynomials? If they are polynomials, what is their degree? And I guess I can define degree, but maybe we'll define it after we even talk about this a little bit. Now, I should say the degree. The degree on a polynomial is the highest power of x you see. So, here are some polynomials. Here are some functions. Tell me if they're polynomials. If they are polynomials, tell me their degree. So the first example. 5. Is 5 a polynomial? Folks who want to say yes? Any folks who want to say no? Cool. It is in fact a polynomial. What degree is that polynomial? 0. Constants are degree 0 polynomials. Degree 0 polynomial. 1 over x. Is that a polynomial? Think on this for a moment. And now let's just see what your intuition is. How many people would want to say yes? How many people would want to say no? Cool. Those of you who would want to say yes, what degree would you want it to be? -1. That's certainly a good intuition, but a polynomial is only allowed positive powers on x. This is still a perfectly good function. It's a different thing than a polynomial. It's what's called a rational function. And we have this distinction because 1 over x will really have some different behaviors from polynomials. Like it'll have some vertical asymptotes. Next one on the list. 4x to the 5th minus x to the 1, that one. Is that a polynomial? Folks want to say yes? Yeah, right, of course it is. It's like, it's literally a sum of powers of x. What's the degree? 5. Yes. Degree is 5. Next one. No, that's the next one. x to the power 1/2, so the square root of x. Is it a polynomial? Folks want to say yes? Any folks want to say no? Cool. You said, those of you who said yes, what degree should it be? I guess 1/2 is probably the intuitive choice. But what counts as a polynomial is only functions with whole number powers of x. So like I'm putting these trick questions here because like these are the obvious trick questions. Like these are things that'll trip you up. This doesn't count as a polynomial. Again, it'll have some different behavior from polynomials. Not a polynomial. X plus 1 over x minus 1. Polynomial or not polynomial? Polynomial? Not a polynomial. Cool, yeah, you're not allowed to divide by x's. You're only allowed to add up non-negative powers of x. It's the same type of function as 1 over x, it's what's called a rational function. Next one, x plus 3, x plus 2, x plus 1. Is it a polynomial? Anyone want to say yes? Anyone want to say no? Cool, yeah. What's the degree? 3. It's not already written as a sum of powers of x, but you could like FOIL that out, right? I guess you could FOIL it out would be the first step, and then the second step when you see something that's like 3 terms long and 2 terms long, the acronym FOIL doesn't make sense anymore, but I guess like the box method still works. You could expand it out. Degree equals 3. Last one, 2 raised to the power x. Would you want that to be a polynomial? Folks for yes? Folks for no? Cool, yeah, it's not. It's a different type of function. It's what's called an exponential function. Polynomials, you're allowed to have exponents, but only whole number constants in the exponent. All right, so I've done some like identifying polynomials. What I want to do in this first bit of packet is just like some graphing. We'll notice some patterns about polynomials. It turns out even as soon as the degree of the polynomial is 3, the graphs get a bit more complicated than their quadratic cousins. But you can still notice some patterns. So, here are some graphs. If on your own time you want to go and bust out Desmos, this QR code in fact leads to a Desmos demo with these things graphed. You can also just open up Desmos and graph them. So let's just answer some questions about this. So that first one is just the graph of x cubed. We've seen that before, right? That's a power function. Let's answer some questions. How many roots does it have? Just the one? Here are root, x-intercept, and a solution to f of x equals 0 kind of all mean the same sort of thing. So it has 1 root, but it kind of has like 3 roots all at the same time. And so there's like, we'll explain this buzzword on Monday. The multiplicity is 3. It's got 1 root of multiplicity 3. Don't worry about the multiplicity for now. This next function, x times 2x squared plus 1. How many roots or x-intercepts does it seem to have? Still just the 1. But it's like a different sort of looking root. It looks like it crashes straight through the x-axis instead of kind of slowing down and resuming on its way. So this one has, honestly, just 1 root. Of multiplicity 1. Next one, x times x minus a third times x plus 1. How many roots does that seem to have? 3? 2 of them are kind of close, so maybe it's hard to see by looking at the graph, but it actually dips below the x-axis a little bit. 3 roots. This next one, well, you can zoom in by like just looking closer at your paper too. X times x minus 1 squared. How many roots does it seem to have? 2. I think there's one and there's one. That one looks like it might be multiplicity 2, in that like it looks like it's bouncing off of the x-axis. 2 roots. Neato. We got enough time to talk about taunting points also. So let's count up how many taunting points these polynomials have. Yeah, 2 minutes. So the first, x cubed. How many taunting points?
I hear a 1, and it's kind of a taunting point, but is it actually taunting around there? No, like, slows down and stops, but then it keeps on going. So technically, I'd want to count that as no taunting points at all.
But I get why you would want to maybe count it as like kind of a taunting point. It's certainly what you would call in calculus a critical point.
But we won't talk about critical points. This isn't calculus. We don't need calculus. Next one. How many taunting points does it have? Yeah.
Returning points directly correlate to roots when it roots around.
There's a relationship in that.
If you have more than one root, will you have a turning point?
Well, let's see. So let's suppose you had 2 different roots. Well, I'd have to be coming up and coming back down in order to get back to the other one. So I think, yeah, you'd have to have at least one taunting point. Maybe more. And we'll see this in the thought example, the example in the thought column. So yeah, maybe let's go right here. How many taunting points does this seem to have? 2. There's 1 in between those 2 roots, 1 between those 2 roots. So in between 2 roots, there will definitely be a taunting point. There might be more than one. And let's just finish it up. That first one, how many taunting points? 0. And there's not even temptation. It doesn't even stop at x equals 0. It crashes straight through. This last one, how many taunting points? 2. One of them's at a root. So notice, I think a root of even multiplicity is probably going to be a taunting point. Nice. Cool. So, what will we do starting next time? We'll take those same graphs and we will just zoom out. And we'll notice something. Do all those graphs now look pretty similar to each other? Yeah, so like if you zoom out on a polynomial, they tend to all look the same. You too.
Ooh, stop the recording.